Hello students, in the previous lecture we had defined a cyclic group and discussed with the example or with the help of examples that what cyclic group is and discuss its generator. A cyclic group can have more than one generator and also drive the theorem that a finite group in a finite group a finite group contains an element of order n. If a finite group contains an element of order n, then that is cyclic. Now, in this lecture, we'll drive the second lecture of on this cyclic group. In this lecture, we'll drive more theorems on cyclic group. The first theorem is prove that every cyclic group is abelian. So it is a group. Cyclic group is a cyclic group. First is a group. We did satisfy all the four axioms. Now we have to show that if the cyclic group, if a group have only one generator, then we are able to show that that is abelian means commutative group we also hold on. Now given is let G be a cyclic group generated by A generator of this. So we can write this as and G is equal to this is equal to A using this variable. So let us take two elements x and y belongs to G and two elements. So if the x and y belongs to G and A is generator of A is generator of G and G cyclic, therefore we can write x is equal to A power m and y is equal to A power n for some integer m. Cyclic group generated by A. The elements of A are G are A square, A cube, so on to so on, so on. A3, A4, so on. Now, our aim is to show that this is a abelian group. So let's find the product of these elements. These two elements belong to G. Find their product x into y. Substitute the value h by m into h by n. H by n is equal to base is same. This is we have proved this that h power base same power 8. So now the power m and n are integers. So integers commute. M plus n equal to n plus n. We can write here because they are integers. So h power n is 1. Now again indices in the reverse order. So h power m into h power n. Substitute the value y into x. So xy belongs to G, and we have proved that xy is equal to yx implies G is abelian. But the converse of this theorem is not true. That is, every abelian group is not cyclic. So let's discuss an example to show this. So let us consider the set of rational numbers with binary composition of addition. It is not a cyclic group, but it's a abelian group. So we have to consider the set of rational numbers with the binary composition addition. And we'll show that this set of rational number we have proved that this is a abelian group under the operation of addition. Now I'll show that it is not cyclic. So proof is by contradiction. Let's take a rational number of type m by n. Now m and n both definition of rational number. M and n both are integers, and m and n are related to prime, and n is not equal to 0. Is generator of, so that it has a generator of the type m by n belongs to Q. If this Q has a generator under the binary composition addition, then every element of Q is the integral multiple of m by n. So let us take another element 3 by. We can have so many examples, but I'm taking 1 by 3n belongs to Q. So now this element, if this Q is cyclic, then 1 by 3n can be written as k times m1n for some integer k. So now cancel out n from them and simplify it. So we from this we got k into m is equal to 1 by 3. But k and m both are integers, so their product can't be a rational number, which is not possible because both are integers, so their product can't be a fraction. Hence, no element of Q can be expressed as integral multiple of m by n. So implies no element of Q can act as a generator of Q. So we prove that this set of rational number in the binary addition was commutative, but it does not contain a cyclic. The next one is prove that the order of a cyclic group is equal to the order of its generator. That order of cyclic is the order of its generator. So let G be a cyclic group generator. Whose generator is A. So we can write this. So what to prove? Or we need to prove that order of G is equal to order of A. So two possibilities rise. Uh, G can be finite or G can be infinite, or G can be finite set or G can be infinite set. If G is a finite set, then order of A, order of G infinite, order of A will be finite, which generates G. So first possibility is let order of A is finite, means G is a finite set. If order of A is finite, then there exists a positive integer n such that order of A is equal to n. That is, A is equal to order of A n implies A is equal to G. Since A belongs to G, so since A belongs to G, so A square, so on to A power n minus 1, and is equal to E, all belongs to G. Because G is cyclic group, cyclic group, order, cyclic group. Now our aim is to show that that these are the only distinct elements of G. That is, we show that G consists of these elements A square, A to so on this power, A n minus 1, and this one is equal to subcase first. Let us prove that. We will show that they are distinct. So we are proving the contradiction. So let us prove that two elements of G are equal. So AI is equal to AJ, both belong to G for some I in J. One is less than equal to J is less than I is less than this convention. We have convention using this. So if they're equal, because G is a group, first for a group cycle it is a group. So in a group, cancellation law holds true. So apply that cancellation law. If J belongs to G, then it's to minus J. Notes of J is to minus J. Also belongs to G. So apply right cancellation law with the of A is minus J. So this is equal to A is power I, combine them, A is power I minus J is equal to A is power J minus J 0 is equal to B. So now we got A is minus Ij, minus Ij. Since 1 is less than J is less than I is less than N, therefore 1 is less than J, I minus J is less than N. That's equal. So that's this. They are the one and set. So therefore, A is for I minus J is equal to E, where I minus J is the positive integer less than N. The order of A was how much? It was N. So it contradicts, which is contradiction that the two elements of G are equal. Implies no two elements of these are equal. Elements of G are equal. So therefore, all the elements of G are distinct. Now second case, second. Uh, now our in the second, now our aim is to show that these are the only distinct element of G. First, we shown that there are no two elements of G are equal. Now our aim is to show that uh, these are the only distinct element of G. Which one? A square, A cube, so A and so on. These are the only distinct element of G. And so J is what? That is, any element of G is equal to one of them. And element G, if you take any element G, that will belong to from A square, so to A to n. So let us take an element x belongs to G. Be an arbitrary element. This element is out of one of these elements. Suppose that x is one of these elements, A square, so to A square. So means if it is any one of them, then therefore x simultaneous is for m for some positive integer m can be equal to 3 element number. So if A is for M is any element belongs to G, then by division algorithm order of A is n, so n must divide m. Must if it is not out of them, so this integer greater than n, so you must divide by n. So by division algorithm, there is this quotient and remainder such that m can utilize divide m by n is equal to r, m is equal to n q plus r by division algorithm, where r is will be less than remainder will be less than less than equal to r. Now substitute the value of a x is equal to a for m is equal to a for m q plus r, a is for n q is for r, a is for n is for q is for r, a is for n is equal to e because order of a is equal to n is equal to a r. Implies x is equal to a is for r, where 0 less than equal to r less than n. Implies what does this imply? X is one of the elements these elements less than n. X can be is equal to r, you can take to 1 to 0, e identity element 1, a 2 so to. Therefore, these are the only distinct element of G. Implies order of A is equal to order of G. Now, second case, if order of A is infinity. If order of A is infinity, since A belongs to G, so the infinite elements A square, A cube, so much to infinity belongs to G. Close property because G is a group. Now, our aim is to show that no two elements, no two of them are equal. Proof is by reduction. We suppose that two elements of this are equal. Let's suppose that A square R is equal to A square S. There are two elements of G and two elements of G for some integer R and S such that the convention R is equal to. So assume that R is equal to S. Now again G belongs to G. G is a group, so cancellation holds true. So apply cancellation over here. This will go to this can written as A for R. Apply cancellation over is for S is belongs to G. A for M is for minus S so belongs to G. Inverse of A for S. So apply cancellation law. We got A is for R minus S is equal to A for S minus S is equal to G. Where S R minus S is a positive. Therefore, order of A is a finite. Two elements are equal, then order of A comes out finite, which is a contradiction. Order of A is infinity. Our solution is wrong. Hence, none of the two elements of this are equal. Therefore, G is a infinite group. G is an infinite group. Order of G is infinity. Order of A is also infinity. So, order of the are equal. Next is we'll show an example. Show that the set of we have repeated this example. You must calculate the roots of an unity. It was very clear about the unity. We have repeated this many times. Show that the set of n group of unity form a cyclic group under the binary composition multiplication. Composition multiplication, G is the set of n. So G is consists of set of n when that is G consists of E is for 2r and iota upon n. 2r pi iota upon n is called this. Where r 0 is less than equal to r less than n or less than equal to n. These are n. And how many roots are there? They are 0 to n minus 1 n roots. So our aim is to form a abelian group under the binary composition of multiplication. So let us assume x to be equal to 2 pi I upon n. If x is this, then G will take the form. You take the form e power r x such that 0 less than 2 r less than equal to n. So what are the elements of G? They are as with 0, as with 1, so on to 1 is for x equal to x equal to 3x is equal to n minus 1. So what is this? This is a cyclic group of order n. How many elements are this? So this cyclic group of order n generated by e for x. So generated e for x. So since e power rx is equal to e power x power r is from minus 1, therefore and e power nx is equal to 1. Imply cyclic group. The group of n-th under the binary composition of multiplication is a cyclic. Now the next question is, show that G consisting of these four elements 1 to 4 form a cyclic group under the multiplication modulo 5. Given a G is set of these four elements, composition defined on G is multiplication modulo 5. That is when we multiply A and B divided by 5, remainder is 1. Remainder is equal to R. Or we can also write it as AB is congruent to R modulo 5. This can be as AB is congruent to R modulo 5. Here is the remainder when AB is divided by 5. Now, write 2 raised to power 2, 2 plus 2 into 2, 4 divided by 5 is equal to 4. Remainder is 4. 2 is a 3, 2 addition modulo 5 plus 2 addition modulo 5 plus 2 addition 5, 2 into addition modulo, sorry, 2 addition modulo 5, 2 addition modulo 5, 2. Is it 2 is 3? Okay, 3 is equal to this 2, 4, 8 divided by 5 is equal to 6. So 4 is equal to, when 8 divided by 5 is equal to 1. This is 16 by 1. So 5 is equal to, 5 is equal to 2 into 2 into 2 into 2 multiplied by 5 times divided by 5 is equal to 3. So this is 1, 2, 3, 4. 2 power. So 2 is the generator for this. We will move down to this and 2 left than 2 power 2 5 and 2 4. 2 power 1 is equal to 2. 2 power 0 is equal to 1. So 0 is equal to 2 is 4 is equal to 1. So 2 is the generator for this. Similarly, 3 is for 3 into 3, 9 divided by 5, 4. 3 is equal to 3 power 1 is equal to 3. So 3. 3 power 4 is equal to 3 is equal to 3 into 3 is 3, 9, 27 divided by 5 by 2 is in there. So 4, 81 divided by 5, 1. 243 divided by 5 is equal to 3. So 3 is power this. It's power 2, 1, 2, 3, 4, all the numbers. So 3 is power 2, 3, 4, 5. So this is a generated by 3. So generated by 3. Since every element of G can be expressed power of 2 and 3, so they are generated. So means a cyclic group, we have in the previous lecture also told that a cyclic group can have more than one generator, more than one generator, and can have more than one identity element. Can have more than one generator, not identity, but more than one generator. So G cyclic group generated of order 4 generated by this 2 and 3, because 2 is power 3 is power 4, 4 element 1, 2 is power 4 equal to 1. So order of group and order of element same. So this is order same. This is cyclic group generated by 2 and 3. This example also implies the cyclic group can have more than one generators. Again, let G be a group cyclic group of order 8. Let G cyclic group of order 8. Find how many generators. Now, question is, or they can have only 2 or more than 2 generators. So how many, which are generators of cyclic group? Now, in the proceeding study, will make these things clear. Find how many generators are there. So given is G cyclic group of order 8 and let is generator. So we know that in the cyclic group the order of a group is equal to order of generator. So order of we have proved this to. Order of group is 8 element. Order of generator must be 8, means A for 8 must be equal to E. So let's consider. So given 8 elements, so group will be A generated by A is placed onto A file. Since 3, 7 and 8, the indices of 3, 7, 8 are relative prime to 8. So therefore, A is for 3. Now in the previous case, this 2 and 3 are relative prime to 5. 4 also. 4 can also generated from this. 4, 2 is relative prime to 5, 3 is relative prime to 5, and 4 can also have a generator for this. Which is the 4 is So to this is for 3, is for 5, is for 7 are also generator of G. So this have 4 generators. Okay. So numbers, we found the generator of the, or if you come find the generator of any finite group, then the numbers, then the, if in the case of multiplication, the indices relative prime to the order of generator will can act as a generator. For this example, show that the group consisting of these uh, numbers, these prime numbers 1, 5, 7, 11 of integers under the composition multiplication order 12 is not a cycle. Not a cycle. So now we got is for 5, so 2, 25 divided by 1. Limits 7 is for 2 is equal to again 1. 11 is for 2, 121 divided by 2 is equal to 1. Here we don't find any element of G whose order is equal to the order of the group. So for any group 2 cyclic, we must have at least one element, or at least one element of the G which can act as generator. So we don't find whose order is equal to order of group. So this group is not a cyclic group. Thank you very much.